Hello friends, today I am going to discuss the difference between conservative and non-conservative forces. What is the actual difference? What are conservative forces? What are non-conservative forces? And what is the physics behind them? So let's start. So in our day-to-day life we have this word conservative and sometimes we read non-conservative. So the conservative forces are those forces due to which the work done in a closed path is zero. It is the very basic definition. Let's say this is a closed path and this is the starting and the final point A. So due to this force, the work done by this force is equal to zero if in closed path. So we can say that this force is conservative in nature. So F will be conservative. We will discuss more about it. So which are the examples which are very much suitable for the conservative forces and which are the examples which are suitable for non-conservative forces? So in our day-to-day life, in our physics, the very first is electrostatic force. Electrostatic force is conservative in nature, and the other example is gravitational force. Gravitational force is also conservative in nature, and you may heard about the elastic force, that is the force due to stretched spring, right? So spring force, we can say spring force. So these are the three very basic examples which comes under the conservative forces. We will discuss about it a little bit, why these are conservative in nature, and the examples for non-conservative forces are those like the frictional, which is your favorite one. The frictional force is non-conservative in nature. Okay, and next we can say the force arises due to the fluid. When a body moves in a fluid, for example in air or in liquid, the resistive force which applied on the body due to that fluid is also non-conservative in nature. So we can write here fluid force is also non-conservative in nature. Okay, these are the very basic examples. So let's discuss further regarding these forces. So firstly, if we talk about the conservative forces, so conservative forces has a very basic definition which I have already discussed, that is the work done in a closed path is zero. So work done by the conservative forces in closed path is always zero. Why it is zero? Let's take an example. Let's say we have a ground and an object is moving upward up to this height. Okay, let's say this height is 20 meter. Okay, all right. So what is the work done by the gravitational force here? Let's say this is 2 kg object. So gravitational force is acting downward. Gravitational force, which is mg, is acting downward, but the displacement of the object is upward from A to B. Okay, so work done by the gravitational force in taking the object here is mgh, right? Gravitational force multiplied by displacement. Gravitational force is downward direction, so it is minus mg, and displacement is in the upward direction, which is 20. Let's put the value, it is 2. Let's put g is equal to 10. Okay, and 20. Okay, so this is gravitational force here. So if we solve this, it comes out to be minus 400 joule. This is the work done by the gravitational force in taking the object from A to B. But in the downward direction, when the object moves from B to A, then what is the process, what is the work done by this gravitational force? Let me discuss it. So now the displacement is in the downward direction. Again it is 20 meter, but the direction is downward. Gravitational force is also downward. It means that the displacement and force acting in the same direction. So work done 2 is equals to force, which is minus mg, and displacement here minus 20 because of downward direction. So minus 2 into 10 minus 20, minus minus becomes positive, so it comes out to be 400 joule. So we see that here the work done 1 is equals to work done 2 in magnitude but opposite in nature. So the total work done, if we see the total work done here, total work done total is equal to work 1 plus work 2, which is minus 400 plus 400 joule. So it comes out to be 0 joule. So this is the very suitable example to define that work done by the conservative forces in a closed path is always 0. Okay, so this is one of the definition. Also we define the work done as work done by the conservative forces can also be written as negative of the change in potential energy, that is change in delta U, change in potential energy. It means final potential energy minus initial potential energy, like this. It is very easy calculation. We can verify this result with the help of above example 2. Third thing about conservative forces is that the work done by the conservative forces is independent of path. Okay, so work done by the conservative forces is independent of path taken. What it means? It means that if the object follow this path, path 1, or the object follow this path, path 2, in both the paths the work done either along the path 1 or along the path 2, the work done will be same, work done will be same under one condition, and the condition is if the forces acting on the object is conservative forces. And it is very easy to calculate such situations. We can solve such situations with the help of the above example. Under the gravitational force examples, we can see that the results comes out to be same. So we have this situation, this one situation, and the other one is it is independent of the path, but it only depends on the initial and the final positions. Okay, so initial position and the final position, it is what matters. It means that if an object follow this path, or this path 1, 2 or 3, initial and final position in all the three paths are same, therefore the work done is equal to 2 is equal to 3 under conservative forces. If these work done comes out to be equal, it means that the forces which are doing the work are conservative in nature. Okay, if I am saying if W1 equals to W2 equals to W3, it means that forces are conservative. Forces are conservative in nature. Alright, so it is independent of path taken but depends on the initial and final positions. One more thing about the conservative forces is that the total mechanical energy remain constant in these situations. Total mechanical energy equals to kinetic energy plus potential energy. It remain constant. Okay, we can take an example to verify this. So the change in mechanical energy is equal to change in kinetic energy plus change in potential energy. As the value is constant, so there must not be any change, so change must be 0. Okay, let's verify this statement with one of the examples. Again, under the gravitational situation, we have an object of 2 kg which is 20 meter above the ground. It is released from height, and when it reaches the ground at point B from A, so we will find out what is its final velocity and then initial total kinetic energy and potential energies. So here K initial and potential initial, and so mechanical energy initial. We will find out these values, then we will find final kinetic energy, final potential energy and final mechanical energy, and then we will verify that is the above statement that the mechanical energy under conservative forces is constant or not. Let's see. So at point A, this is position A, this is position B. So at position A, the object has 0 velocity, so its kinetic energy is 0, but it is at a height of 20 meter, so initial potential energy is equal to mgh. M equal to 2, let's put the value of g is 10 and h is equal to 20. It comes out to be 400 joule. Okay, initial potential energy. Okay, so what about the initial mechanical energy? So initial mechanical energy is nothing but the initial kinetic energy plus initial potential energy. So kinetic energy is 0 and potential energy is 400 joule, therefore the total is 400 joule. So the initial mechanical energy is 400 joule in this example. Alright, now we will find out the final kinetic energy, final potential energy and final mechanical energy. Let's find out. So here, as the object is falling from 20 meter height, so the final velocity square equals to initial velocity square 2 a d. This is the third equation of motion. So final velocity square equals to 0 plus 2, acceleration is equal to minus 10, and displacement is also in the downward direction, so we will put minus 20. When we solve this, it comes out to be negative negative positive, and this comes out to be positive 400. So the final velocity is nothing but under root of 400, which comes out to be 20 meter per second. This is the final velocity. Okay, therefore the final kinetic energy is nothing but 1 by 2 mv final square. Let's put the value, m equals to 2 kg, v final is 20. When we solve this, it comes out to be 400 joule. So the kinetic energy is 400 joule, final kinetic energy, and the final potential energy is 0 because mgh, and the value of h at ground is 0. Okay, so the total mechanical energy, the final mechanical energy is equal to final kinetic energy plus final potential energy. Final kinetic energy comes out to be 400 joule and the final potential energy is 0. So the final mechanical energy comes out to be 400 joule. Therefore, we can conclude that the initial mechanical energy equals to final mechanical energy equals to 400 joule. And if this happens, it means that it is happening when the force is only gravitational force. So we can say that under conservative forces the mechanical energy of the object is constant, or the mechanical energy of the system is constant. So there is no change in the mechanical energy of the system. So change in mechanical energy under conservative forces is always zero. Very, very important. Change in mechanical energy under conservative forces is always zero. Okay, so this is very important point and we have verified this. Alright, so let's discuss about the non-conservative forces. What are non-conservative forces, and with few examples. So non-conservative forces, as one of the very best example is frictional force. Non-conservative forces. So here let's say this is some wedge and an object is moving upward. When the object is moving upward, it is some theta, okay, and this is right angled. It's a very basic example. When the object is moving upward having some mass, then the frictional force acts in this direction, okay, but the displacement covered by the object is in this direction, upward direction, along the inclined plane. As we can see from the diagram that the force and the displacement direction are opposite, it means that the work done will be negative. Work done will be positive when the direction of displacement and direction of force is along the same direction. So here the work done by the frictional force as going upward along the inclined plane is equals to negative. Let's say it's minus 100 joule roughly, without any further calculations. We are assuming it is minus 100 joule. Okay, the same situation arises when this object fall or comes down, something like this. Now the object reaches here and it is moving in the downward direction. So in this case the direction of displacement is downward along the inclined plane, but the direction of applied friction between the wedge and the object is in this direction. Again the displacement and the force has opposite direction, so the work done by the frictional force on the object here again negative. So work done by frictional in this case again negative, and let's say it is again minus 100 joule. So the total work done in the round trip as the body moves up and the same displacement is covered in the downward direction, right? So the net displacement is 0, but total work done is equal to friction 1, work done by friction 2, it is equal to negative and negative 100. Negative 200 joule is the work done by the friction in this example, as it is a closed path, right? Because the initial position and the final position of the object is same, but the work done is not 0. Therefore friction is not categorized under the conservative forces, because we know that in the conservative forces, the work done along a closed path must be 0. So here we see that in this example, the work done by the friction in a closed path in a reversible path is non-zero. Okay, that's why friction is under non-conservative forces. Okay, one more thing we can discuss about the friction under the non-conservative forces is that in this case the mechanical energy is not conserved. Let's consider it with this example. I am saying mechanical energy is not conserved. Mechanical energy is not conserved in non-conservative forces. Let's say again, this is the ground. We have an object and this object is moving in the right direction. Therefore, the friction will act in the opposite direction, right? So, as it is moving on the ground, so the potential energy here, initial potential energy is 0 joule. Let's say here the initial kinetic energy is equal to, let's say, 100 joule here at position A. So the total mechanical energy or initial mechanical energy is equal to initial kinetic plus initial potential energy. It is 100 joule plus 0 joule is equal to 100 joule. This is the initial mechanical energy. Due to friction, the block decreases its kinetic energy and finally comes to rest. Okay, we know this in our day-to-day life. Let's say the block comes to rest at this position B. So here its velocity becomes 0. Okay, it means its final kinetic energy becomes 0. Again the block is on the ground. It means that its potential energy is also 0. So the mechanical energy final is equal to K final plus U final. 0 plus 0 equals to 0 joule. So what we see? We see that in this system the mechanical energy is not conserved, right? But under the conservative forces the mechanical energy is conserved, and we saw it in our earlier example. So this is very important. This statement is very important, that mechanical energy is not conserved in non-conservative forces. One more point we need to discuss is that there is no potential energy function is described for the non-conservative forces. So there is no potential energy function defined for the non-conservative forces. Okay, it is very important, as in the conservative forces what happen if the kinetic energy decreases, that decrease in kinetic energy converted into increase in potential energy, and when the system reverse its direction, that potential energy again converted back into kinetic energy. So that is the reversible processes happen in under the conservative forces. But here once the kinetic energy decreases, that decrease in kinetic energy is not going to stored in the form of potential energy under non-conservative forces. Okay, and we have seen this example here, as the kinetic energy of the object decreases from A when it moves from A to B. That decrease in kinetic energy, that lost in kinetic energy is not equal to the gain in potential energy. The potential energy remains 0, but the kinetic energy also lost of the system. It means that it is not a reversible process. There is no potential energy function associated with the non-conservative forces, and there is no reversible path concept happen in the non-conservative forces. So keep in mind, the loss in kinetic energy cannot be recovered by reversing the motion or in any other way, and the mechanical energy is not constant, and there is no potential energy function for the non-conservative forces like frictional forces. Okay, so the work done by the non-conservative forces cannot be expressed in terms of potential energy function, as the work done by the conservative forces can be expressed in terms of potential energy function, but here for the non-conservative forces, work done cannot be expressed in terms of potential energy function. Okay, so usually we see that due to these non-conservative forces like frictional forces or the fluid resistance forces, the mechanical energy decreases. As in this example, we see that the mechanical energy initially is 100 joule, but finally the mechanical energy becomes 0 joule. It means that the mechanical energy decreases. So these forces are also known as dissipative forces, right? What we call these forces also known as dissipative forces, because the mechanical energy decreases. But there is an example, there are few situations when under the non-conservative forces the mechanical energy of the system increases. Let's discuss that example. So it means that there are situations under the non-conservative forces when the mechanical energy of the system decreases, and those forces are known as dissipative forces. But if the mechanical energy of the system increases, those forces are also known as non-conservative forces, but it happens, and that happen when we can see that in firecracker situation. As there is a firecracker, once it blasts, its particle move with very fast kinetic energy in the upward direction, so they have very high velocities, and they are also above the ground. It means that the particles of these firecracker, the fragments of these firecrackers, gain kinetic energy as well as potential energy. So they gain kinetic energy as well as potential energy, but initially the kinetic energy is 0 as well as potential energy is 0. But after some time, once the chemical reaction takes place and the forces arises due to that chemical reaction is non-conservative in nature. Here initially the mechanical energy is 0, but in this situation the mechanical energy not equals to 0. It has some value, it has some positive value because of the kinetic energy of the fragments as well as the potential energy, because it rises from the ground. Alright, so here the mechanical energy increases. So the forces arises due to the chemical reaction. Force arise due to chemical reaction. Okay, and this force is non-conservative. This force is again non-conservative in nature, keep in mind, and this is also a non-reversible process. We know that these fragments does not reassemble themselves into a very big firecracker, we know that, right? So this is a non-reversible process. Okay, let's analyze what is the work done by the non-conservative forces, how to calculate the work done by the non-conservative forces in numerical. It's a very easy mathematics here. So from the work energy theorem, the total work done or net work done is nothing but change in kinetic energy of the system. Okay, of the system. This is from the work energy statement. Total work done of the system is equal to yeah, or we can say the total work done by all the forces, all forces, either conservative, either non-conservative, all the forces is nothing but change in kinetic energy of the system. This is work energy theorem. So what it says, the total work done, it means that work done by conservative forces, work done by non-conservative forces, and total work done from the work energy theorem is equals to delta K. Work done by the conservative forces is nothing but change in potential energy of the system, and from this mathematics we can calculate the work done by the non-conservative. So it comes out to be delta K plus delta U equals to work done by non-conservative. So this is the work done by the non-conservative forces. Okay, so delta K plus delta U is nothing but delta M, as kinetic energy plus potential energy is equal to mechanical energy. It means that change in kinetic energy plus change in potential energy is nothing but change in mechanical energy. So work done by the non-conservative forces is equal to the change in a mechanical energy of the system. It is very important, we should keep in mind this statement. So this is all for the today's lecture. I hope you will understand what is conservative or what are non-conservative forces. I have tried my best. If you need any further help regarding any topic, just mention it in the comment section, so I will try to make that lecture on that topic. Wish you all the best and stay tuned. If you are new to my channel, please subscribe it, share it and like it. Bye bye.